Bismillahirrahmanirrahim, everyone. Uh, Welcome to our second recorded lecture, Mechanics of Material. Last day, we had one long lecture, about 50 minutes, discussing and reviewing the chapter 3, that is about the Torsion. And we did some examples, and then we did some handwritten examples as well, and from the book as well. Unfortunately, there was two issues. One issue was the technical one, that was I could not switch or the share my slides with you guys after the hand notes written in the OneNote software. So I send my presentation as well, so that you can see those slides while watching my lecture or listening my lecture, whatsoever the case is. So I hope you will tally those presentation with my discussion, and you will be able to understand what is happening all about. Second thing was a technical. Second thing was a theoretical aspect. I just want to share the one with you. In the end, if you remember, we discussed one shaft like this one, that we have one shaft over here, and that is under the influence of 200 Newton meter and 500 Newton meter torque, and then fixed at both ends. And statically, when we took the equation for it, it is minus TA plus 200 plus 500 plus TD equals to minus TD equals to 0, because TD and TA are in the clockwise direction and rest of two are in the anti-clockwise direction. Right, TA plus TD is equal to 700. So statically indeterminate problem reason behind, we have two unknowns and one equation. So from where the second other equation will come. So there are two methodologies. One is superposition method and another one is the generic method. I discussed in detail the generic method, right? That we will remove these two fixed from there, and when it will have counterclockwise 200 and 500 Newton meter torque applied at point B and C, so it will cause clockwise TA and clockwise DA at the supports or the fixed points, that is the A and D over here. So, since TA is unknown to us, so in section AB it will be TA, in section BC it will be 200 minus TA, and in section C and D it will be from this section will be TA 700 minus TA, right? And since these 2 points, this point A and this point D are fixed one, so they will not move any point. So net angle of twist at this point A and D will be 0. So what we will do, we will add all the angle of twist, like phi A, point A with respect to B, and point B with respect to C, and point C with respect to D, and we add all these and equate is equal to 0. Now we know what the equation is, that this is TL over GJ. TL over GJ, TL over GJ, right? So L is known, whatsoever that is. G is the modulus of rigidity. J is basically second moment of area, or the moment of polar moment of inertia. Again, we know how to calculate all this. This is the fixed value. J is fixed. J is fixed. L will be fixed, whatsoever that is. J we know for a solid rod how we calculate it. Now this torque will be in first phi A B will be TA, in phi for phi BC it will be 200 minus TA, and for phi CD it will be 700 minus TA, and you will put and you will calculate and you will get the TA from there, right? And that TA will come in this equation over here, and you will calculate TD. Last time what I did, I said that TA will be in terms of TD, like the one we did here in this example, but it will not be the case for the generic one, right? So you will straightforwardly get the TA from this equation, and then you will put that TA into this, and you will get TD directly from there, right? So this was the correction I just want to make over here. So let's start from page 5, right? So this is specifically the gears, right? Because the gears are the very most equipment or the component in machines. And I hope you remember what is what why we use the gears. We primarily use the gear for the transmission of the power, right? So transmission of power means that you have a motor, for example. You have a motor over here like this one. You can say this is a motor, and it would have some capacity that may be in terms of HP and kilowatt, right? So this HP and kilowatt we will see in the end, that how we can calculate in form of torque, right? We will give you standard expressions from where you can calculate torque of a motor having certain HP or the kilowatt, right? This motor will produce TM, torque produced by the motor, and that torque will be transmitted to, for example, a gear A. Gear E is a smaller one, and then you have a gear B, that is the larger one. So, right? For example, you can say the size ratio of A B is 1:3. So what will happen then? The total torque that will be generating by this motor will transmit to TA, right? So TM will be equals to TA, that is say that is, we assume that is 600 pound fit, right? So now the question is, how much torque will be shifted from A to B? Will it be same or it will be different? Definitely it will be different. Reason behind, there are the size difference between the two. One is smaller one and other one is the larger one, right? So the torque that is produced by this 600, that is the motor, and then motor directly attached to this gear A. So all of the torque of the motor, that is 6 pound fit, will be transferred to A. But now the A will transfer larger amount, the same amount to this gear B. But since the gear B is larger in size, so it will produce more torque, right? But then definitely we will have to compromise on the speed of that one, because it will be running at more speed, and that larger gear will be running as the at the lower speed, obviously. If you remember, you use the car, okay? Car mein when you need to go uphill, okay, then you have to come on the downside of the gears, like first gear or the second gear. What you get more power in first and second gear, but lesser RPMs, or the lesser speed of the motor, of the car, right? And when you are going on a smooth road, you go to fourth and fifth gear. There you need lesser torque, but you need higher speed. So gear is a mechanism, gear is a component which produce or the transmit torque from another one body to another body. In this particular case is the motor, and then and then increase or decrease the torque accordingly, and compromise and accordingly you have to compromise on the RPMs of that particular machine, right? So if you remember, just a minute. Right now, so if now we suppose that that the ratio of the gear 1 and gear 2 3 is gear A and gear B is 1:3. So if gear A is producing 600 pound fit, so what will be the TB? What will be the torque that will be produced by this gear B? Since it is 3 times larger than the gear A, so definitely it will go up to the 1800 pound fit. And then you have that TA, that was 600 pound fit, is converted into 1800 pound fit at this particular point over here. Now you have another shaft which have another wheels like W1 and W2. You might have different wheels over there. You might have gears, different gears as well. You might have different component that is being driven by the this gear. So this 1800 pound-feet torque will be shared by all these gears. For example, if one is using 1000 pound-feet, another one will be using remaining 800 pound-feet. So this total torque that is being produced by this gear B, that was obviously 1800 pound-feet, is now being utilized by wheel 1 and by wheel 2, and sum of wheel 1 and wheel 2 torque will be 1800 over here, right? So now we come to another point over here. Now I have drawn two gears. One is this gear A and another one is this gear B, right? This is gear A and this is gear B. Obviously, gear A is basically the smaller one and gear B is the larger one. So generally these two gears mesh with each other. They are in contact with each other. So this point are generally in contact with each other, right? And these 2 points are experiencing a force which is equal but opposite in direction, like this F over here, this one, and this F over here. They are equal and opposite, right? RB, RA, and RB are the radius of these two gears, and because this force is being applied at a distance RA, so the torque that will be being produced by this A gear is F into RA, right? And likewise, the torque that is being produced by this gear B will be F into RB, and RB is the radius of that particular one. Since forces are equal, so we can write F is equal to TA over RA and F equals to TB over RB. This is for the A gear and this is for the B gear, right? Since forces are equal and opposite, so TA over RA will be equals to TB over RB, and if we want to calculate torque that is being produced by B gear, will be RB over RA into TA. So is it increasing or decreasing? TB should be greater than TA or less than TA. Obviously, since this gear is larger in size, so that definitely the torque should be increased when the torque will be transmitted from A to B gear. So size matters a lot, always, right? So a ratio of this RB and over RA will be RB is a greater one, RB is a greater one than RA. So obviously this RB over RA ratio will be greater than 1. So greater than 1 means that TB will be greater than TA, but definitely then you will have to compromise on the speed, as I already discussed with you, that this will be at the cost of speed. Obviously, when you will be moving in the lower gauge, you need more power, more torque, but then you will have to compromise on the speed. And at the higher gauge, definitely you need higher speed than lower torques. So if if you just visualize that what sort of gears will be in a gearbox of a car, then definitely the gears, the smaller gears like gear 1, gear 2 should be larger in size because they are meant for the larger torque but lesser RPMs in comparison with the gears that are being utilized for third, fourth, or the fifth gear in a car, right? So generally you don't need to go for all this. You just have to visualize that what is the larger one. So if the larger one is there, so the larger one will produce more torque than the smaller one. Obviously the RPM will be lesser, because if gear is moving at 300 RPMs, so definitely gear B will not be moving at the same RPM, but it will be producing more torque, right? So now move to next page. So this was basically the torque. Now we come on the phi. We know what the phi is. Phi is basically the relative angular rotation of one end of the with respect to another one. If you remember the rod, we generally give the example that one is fixed, other one is free, and then we twist it because of some torque. So phi comes over there. Phi is basically the relative angular rotation. uh, and definitely that also changes from gear A to gear B. For example, if the smaller gear rotates 1 degree, 1 degree, if this gear A rotates 1 degree, so what do you think the gear B should be? Is it be moving 1 degree, or there should be lesser one? Obviously, this is bigger in size, so it will be moving less than 1 degree if gear one, the smaller one, is rotating 1 degree. So right. So now we come across over here in the mathematics. Right. Again, we have a smaller gear, gear A over here, and then we have a larger gear, gear B over here, right? RA and RB are the respective radiuses of the gear A and gear B. And now if these A point are in contact with each other, right? And when it moves in this direction, in this particular direction, that is clockwise, so from point A to A dash, this is A dash, right? So it will be having some angular rotation, that is phi A for the case A, and phi B will be for the gear B. Now since phi is very small, so phi A, tan of phi A will be equal to tan of phi A, and tan of phi B will be equal to phi B. And what will be the value? Since this is very small, so we can say this arc A dash is assumed to be a straight line, and when it is a straight line, so we can write that A dash over RA for gear A, and A dash over RB for the gear B, right? Since arc length is same, A dash is same for both gear A and gear B, so we can write phi A RA over phi B RB. And phi B means the angular distortion or the angular rotation of gear B will be ratio of radiuses of A over B, gear A over radiuses of A over B, and multiplied by the phi A. So now you can we can look into that if you see that phi B will always be less than phi A. Phi B is the larger gear, phi A is for the smaller gear, right? So because RA over RB will always be less than 1, so phi B will always be less than 5A. And then definitely we can say that because bigger gear is always having lesser lesser rotation, lesser deform angular rotations. So for smaller gear, here is the conclusion: for smaller gear to larger gear, torque increases, phi decreases, and resultingly RPM also decreases, right? So this is how we proceed for the gears. So now we can come, that's all for the gears. As far as this course is concerned, that's done. So we will go in much more detail in the machine design, or you will go in theory of machines, where you will go for all this stuff accordingly. You will read there more about the gears geometries, and then so on and so forth. But as far as mechanics of machine is mechanics of material is concerned, this is done for the gears. So there are two standard formulas, as I discussed in the start, that horsepower or the kilowatts are given generally to the students, and then you need to convert them, because that is the power rating of the gears, and then you have to calculate the torque. So you can directly calculate it with the number of horsepower multiplied by 550 divided by 2 pi f. 2 pi f is basically revolutions per second, or in hertz, and omega, if omega are equal to the rpm, so omega by 60 will be f revolutions per minute. You might see some expression where you can go for pound foot 6600 instead of 550, so that will be pound inch per second. So second will go with the second, and you will end up with only pound feet. In metric system, where we have the watts or the kilowatts powers, here we have a simpler one. Simply divide the watts, that is in the newton meter per second, divided by 2 pi f, so you directly get the torque that is being produced by that particular motor, or the driver side of the machine, right? So, you know,